Yeah, hi everyone. Welcome back to the last day of the summer school. So before today's presentation, I have a quick announcement to make. So we have arranged some special gift for all the posters presenters, and for those who will participate in the flash talk, will pick up their gift on the stage right after their talk. And for the rest of poster presenter, could also pick up their gift at the check-in table right outside the door, like during the coffee break. So for today's presentation, we're so excited to have Professor Andrei Bernevig from Princeton. He will deliver a really exciting talk with the title Mapping of Interacting Flatband with Concentrated Burr Curvature to Topological Heavy Fermion Problem. Please join me in welcoming Professor Bernevig to the stage.
Thank you. I'm even more excited to be here and very happy that some of you have even stayed for this last talk and for the sensational prizes that I'm sure will come with your posters. Okay, so I heard that Ben gave an amazing talk giving all the introduction on twisted bilayer. So I'll just assume for the first part of the talk, and Mike, and I assume for the first part of the talk that everybody's an expert on twisted bilayer, so hence. And then for the second part, for the next talk, I'll assume everybody's an expert on fractional churn insulators. And we're just going to delve right into it. I'll come back to the first slide, which are the people that actually did the work that I'm going to present here. But let's just delve into it. So little reminder of what we're dealing with in condensed matter. We're dealing with single particle dispersions that look something like this. If the Fermi level is, this is two-dimensional dispersion, okay, energy versus momentum. If the Fermi level is here, the system is an insulator. If the Fermi level is in a, in a band, the system is in single particle, a metal. But then what you want to do, as I'm sure Ben and Mike clearly pointed out, is act interactions to all these systems, because interactions really do exist in nature, and that's when the problem gets very dicey because of entanglement and explosion of Hilbert space. So then you basically need smart ways of dealing with the interacting problem in order to solve it. In one dimension, we have integrable systems. That's a smart way of dealing with interacting problems because you have a large set of conserved quantities. In two dimensions, less so, but in some cases, you can still kind of build up on knowledge that was found by 50 or 60 years of condensed matter to get to the answer. So that's what we'll be trying to do here in twisted bilayer graphing, assuming assuming that we do have the single particle physics correctly, and then the single particle physics through a process of deduction and derivation will lead us to an interacting model and a unitary transformation that can map this model into a certain set of degrees of freedom. I want to point out that what Mike basically probably explained theoretically in momentum space can also be obtained in this real space formalism. So the two formalisms are equivalent in terms of the symmetry breaking states. They're not equivalent in terms of the symmetric state, in the sense that this would give you a Kondo picture which cannot be really obtained easily in momentum space formalism. Although if you did it, if you were able to calculate the system to infinity number of states, which are not, then you should obtain obviously the same result. But basically, in the interacting physics, all you're trying to do, because you can't solve the problem exactly, all you're trying to do is make unitary transformation. The quasi-particle basis in a Fermi liquid is just a unitary transformation that basically contains kind of a free particle description. In the beta ansatz is the same thing. So really what we're trying to do in interacting systems is kind of smart choosing of degrees of freedom so that the physics becomes apparent and we don't have to do 2 to the n size diagonalization, which would obviously run out of steam after 20 sites. Okay, you'd run at about 50 sites, you're larger than the number of particles in the universe, so obviously no computer can do it, at least classically, and then you're done. So basically, the moral of the story is that if you can't do the problem exactly, you need to do unitary transformations. So obviously, in condensed matter systems, we have dispersion interactions. For example, this is the band structure of silicon. You can clearly see a large dispersion of around 2 electron volts even of this band. And of course, the interactions are not so important here. So then this one can be described by single particle description, which basically means that the energies are sums of single particle energies, the wave functions are Slater determinants, etc. So this is very simple. On the other side, you have flat bands, and these flat bands basically mean that you have no dispersion, even though your momentum changes. So kind of if you think about the free particle Schrodinger description, where momentum is k squared, energy is k squared over 2m, this violates that because you don't have any change in momentum, in energy as the momentum changes. Of course, it would correspond to m equals infinity, effective electron mass equals infinity, but these bands are not quite m equals infinity, because m equals infinity for flat bands would mean a very trivial band. And actually, you can see that this flat band, for example, in this compound, this flat band has dispersive bands around it. So you know that the hopping of electrons is not zero, okay? And in fact, it's quite large. You can see it's 2 electron volts. The hopping of electrons from one side to another is what gives you basically the bandwidth normally if you don't have flat bands. So you can see that the hopping is very large. But still, one band remains flat. And this is through quantum interference effects. And it's a purely quantum effect of wave functions kind of canceling each other on different sites so that they give you zero dispersion. These are the most interesting type of flat bands because they don't correspond to effective mass being infinity in the sense of not being localized. Effective mass being infinity, if I have an electron of mass being infinity and I put it on a potential, it will stay there because it costs a lot to move. But these bands here, the electron can hop around, except it doesn't gain any kinetic energy as this momentum moves in the Brillouin zone. So these are the kind of bands that we're interested in, and thank God that most of the bands that appear in these twisted samples are of this type. Actually, even if they weren't of this type, they would still be interesting because they would give us quantum simulators for Hubbard models, which we don't understand. But I'm not going to get into that. We can talk about that in private. But basically, there are several types of bands that are flat bands. So as I was saying, for example, in this compound, you can clearly see here a flat band separated by a huge energy, 1 electron volt is a huge energy, gap from another set of bands. And this flat band is basically atomic. So what does this mean? By the way, just stop me and ask questions. You can just either raise your hand or shout, depending on your democratic credentials. Just ask questions as much as you can, please. So basically, this flat band, you can clearly see it here, is separated by a huge gap from the conduction band by a quasi-huge gap from the valence band. So this gap actually corresponds to localized electrons sitting on one of these elements. So what happens here is probably, well, not probably, what happens in this compound is you have some layers which are very close together, whose electrons of the atoms of these layers gives you this dispersion, and then you have some atoms away from those layers whose electrons give you this localized state. This is a state that's not very interesting, at least for the purposes of what we're going to say today. It's very interesting for other purposes, because again, you can do Hubbard model simulators, but for the purposes of today, it's not interesting because it's a localized wave function. There's another type of flat bands, and these are the ones that are, as I was saying, the purpose of the talk today, which come from a lot of hopping, even though you have a lot of hopping. And these flat bands are the topological ones. And why are they interesting? Well, if you've got a topological band, as I'm sure you heard many times in this summer school, you have an obstruction to making this band exponentially localized. You can make it exponentially localized up to some range, but then you have power law decays in the wave functions, and depending on the topology of the band, you can probably have different powers, etc. But you have power laws and the dimension. You have power laws in the wave function, which basically make the band not be localized. Now, I'm sure you are all now familiar with the concept of Berry phases, right? Everybody knows Berry phases. So basically, when you have a Berry phase that winds, i.e., I take the Berry phase in one direction. This is, for example, of 2 occupied bands, of the projection to two occupied bands because I have two eigenvalues. And so I take the Berry phase in one direction momentum space and plot it as a function of the momentum of the perpendicular momentum. If this Berry phase winds, it means that I cannot localize the states. Why? Because the Berry phase is really just the projected position operator. So if I take the Berry phase in the y direction, I just look at how the position of the Wannier states in the y direction varies as the momentum is varied in the x direction. If it winds, okay, it means that there is no way to make the x and y direction projected operators commute, even by any adiabatic transformation, because I don't have, for example, as I move the momentum around here, my y momentum, actually, my y position transverses the entire unit cell, right? This is minus pi and pi are basically the unit cell eigenvalues. So you can see that one Wannier center transverses, this is the quantum spin Hall looking state. But basically, the moral of the story is, if I had half of this, I would have just a Chern insulator. The moral of the story is that as you move your momentum, your y Wannier centers kind of winds around the unit cell. There's no way to break this flow of winding around the unit cell. What you can, the one that would be trivial would be, you know, if the Wannier center would start from here, do something like this, it can, you know, it can have a little dispersion, but come back here without the winding. In that case, you could apply adiabatic transformations and make the x and y projected operators commute and localize the state. Here you cannot, and these are the type of bands we'll be looking at. Nicely, the twisted bilayer bands are of the same type. So I think basically I don't need to introduce this. Twisted bilayer, you take two layers of graphene, you twist them by 1 degree, and magic happens. Magic meaning that graphene by itself doesn't have many interacting effects. Okay, in fact, there are people like Philip Kim and Dima Efetov who are trying to add, because of the zero density of states, trying to increase the chemical potential of single layer graphene in order to, for example, obtain superconductivity. But it's not that easy to increase the chemical potential of an atomic size sample because you need to add a lot of electrons per unit cell. But if you increase the unit cell artificially to, say, 10,000 original unit cells, then adding 1 electron per new unit cell becomes much easier because it corresponds to 1/10,000 electrons per the original unit cell. So adding 1 electron per the moire unit cell, this new unit cell, is much easier now. And this is kind of a new development that flat bands, at least that moire physics brings to the flat bands. Questions? Brings to physics. Okay. So everybody's familiar with this band structure by now? Band structure of twisted bilayer at 1 degree, okay, in some simplified model. Okay, this is the Bissell-McDonald model. You can add things on top of this model, such as strain and relaxation. But the moral of the story is that, as you obviously know so far, you have two flat bands per valley per spin. There's two valleys coming from, you know, the K point of the lower layer and the K point of the upper layer, that's one valley, and the K prime point of the lower layer and the K prime point of the upper layer, that's another valley, and then spin, that gives you a factor of 4, and for each of them you have two bands because you had a Dirac point at every K point, and that's two bands which kind of connect from K moire. This is K moire. All of these plots, all of these axes now are the moire momentas. So much shrunk from the original momenta. And you can fill them from -4 to 4 electrons. Of course, you'd hope that this is a metal in non-interacting physics. And it is a metal because if I fill it with, you know, I'm going to count filling from charge neutrality, which I think everybody counted so far. From charge neutrality, if I fill it, you know, 1 electron above charge neutrality, I'm going to sit in this band. It should be a metal, or 2 electrons above charge neutrality. The band insulator gap is at 4 electrons, so anything at any number of electrons should be a metal. But of course, you look here at filling 2, and you see an insulator. And here you see a superconductor in between at fractional filling, etc. So the purpose would be to explain not only these insulators, which I think Mike explained, right? Hopefully, probably, very likely. I didn't. I was busy taking care of a child, so I couldn't look. But basically, these are insulators which, you know, to varying degrees of complexity. You can describe them by some sort of intervalley coherent states, the IKS state now, as I'll show later. But basically, you want to describe not only these insulators, but more importantly, the state in between these insulators, which is a superconductor, what leads to the superconductor, and the strange metal that appears here. So this is a metal, but it's strange in the sense that it has, you know, weird resistivity, etc., etc. But the moral of the story is really what causes the superconductor, because as you'll see, you have a huge Coulomb repulsion in the system. So how do you screen? How do you cause pairing? So understanding this full phase diagram is the purpose of the physics of TBG, and moreover, hopefully the purpose of understanding, you know, correlated states of matter and the models describing them. When TBG really started, people were very excited because it's such a maneuverable system that hopefully you can learn things about Hubbard models, etc. As I'll show, if you learn anything, it's probably going to be about Anderson models. But you know, it's kind of a laboratory to also experimentally test many-body ideas that are impossible to test with numerics because we can't go that far in Hilbert space dimension. Okay, so very quick recap of the Bicester-McDonald model. I'm sure people have gone through it. This is a large angle. I'm plotting it here. You have the valley K, which is the K of the lower layer and the K of the upper layer, twisted by an angle theta, and valley K prime. I'm not going to look at valley K prime, just at valley K. Valley K have an angle theta. This angle is 1 degree for the flattest bands, around 1 degree for the flattest bands. And this Moiré-Briand zone given by this length scale, i.e. the difference in angles between, the difference in momenta between the valley K of the upper layer and the valley K of the lower layer is called Q1, is just basically the K of the graphene times the angle theta for small angles, and it's a much smaller Briand zone than the original Briand zone. As a result, in order to have these valleys communicate in perturbation theory, you need to fold this small Briand zone a factor of 1 over theta times, because this is, you know, this is a small angle. This is basically very, I drew it very large, but I would have to fold it 1 over theta times to talk to this valley. That's a 1 over theta. That's 100 degree in perturbation theory. So basically, these values don't talk to each other. Valley is a good quantum number, and we're going to treat it as such. And we have spin as also a quantum number. So now the model that you can write down, or the Bicester-McDonald model, you know, you can derive it, but you can also write it down to first harmonic from just symmetries. It's very simple. You can derive it in the two-center approximation, and then you can add strain, relaxation, etc., as I'll show you. But basically, the model, single particle model, is very simple. This is the Dirac sigma dot k in real space of the lower layer. This is at the k point. This is sigma dot k at the upper layer. There should have been a small angle. This should be rotated by a small angle. Turns out that's a 10 to the minus 5 or 10 to the minus 4 change in the band structure, so we're just going to neglect it. And then you have an interlayer potential, T of R, okay, which is a first harmonic in Moiré scale, okay? This Q is this small q, so this is a Moiré length scale modulation, and this is the first harmonic just because you just have basically the difference between, you know, Q1 and Q2, so Q1 is Q1, Q2 is C3 times Q1, and Q3 is C3 squared times Q1. The difference between them are the first harmonic of the Moiré lattice. And so this is a Moiré potential, and this Moiré potential, you can write it down as a hopping between the AA sublattice of the upper and lower layer. It's clear that this shows up upper lower layer. W0 is diagonal. This sigma is not spin, is the AB sublattice of graphene. So what's diagonal here is hopping between this term W0 is hopping between the, or hybridization or whatever you want to call it, between the A sublattice of the upper layer and the A sublattice of the lower layer, and the B of the upper layer and the B of the lower layer, and this is AB hopping, and these are different, and W0 over W1 is of order 0.7, 0.8 in normal samples, or thought to be from ab initio studies. Questions? Yes? This is a two-center approximation. Two-center approximation, all the TMDs would also have no intralayer tunneling, so they will have no potential here. If you remove the two-center, so the TMDs are certainly not in the two-center approximation. Why? Because, you know, they have molybdenum MOT2, right? So MO sits here, they have two TEs here, and you add another layer. So the hopping between the MO orbitals, which are the ones that cause the flat band, happens through the TE, right? Because the TE is actually the one. So that's assisted hopping. Assisted hopping is by definition not two-center approximation. Graphene, a bit two-center, okay? In fact, you don't do much, you don't miss much in graphene if you go away from the two-center approximation. Now, you can add terms which are intralayer, which are strain, etc., relaxation, and we will add them. And they change the band structure, but this is a zeroth order approximation, which is good, whereas in the TMDs it would be a terrible approximation, because I'm sure, as people showed it in previous talks, this term is as large as the interdiagonal term, the intralayer term. There's a potential here, which is what you're referring to. Have I answered your question? Very good, thanks. So graphene, just because you don't have any other orbitals in between, it's just two-layer approximation, two-center approximation, meaning the hopping between atoms is just a function of the distance. If I have assisted hopping, like in MOT2, that's gone. Okay, very good questions. More questions? Okay, so now let's understand these two bands per valley per spin. As I said, there's two bands per valley per spin. -4 to 4 is 8, which is two bands times valley times spin. They can populate 8 electrons. So, obviously we're not going to do, polite people don't do algebra in public, but I can assure you that if you write down the symmetries of this model, of this Bicester-McDonald model, then basically you can prove that for any angle, these bands have to be topological. And it's a very strong statement, and which type of topology has been debated for years, but it turns out that with an extra symmetry of the Bicester-McDonald model, which is the particle-hole symmetry, which is true for the initial Bicester-McDonald model, is not true when you add relaxation, but you can, what we do in physics is start with a simplified model and build up layers of complexity on top of it. So for the Bicester-McDonald model, which is a continuum model, this model is topological at any bandwidth, which is kind of remarkable, because normally, if I have a set of orbitals, the model has to be trivial in the bandwidth of the system. But these are continuum models, which are valley models. Of course, when I reach too high of an energy, 2 electron volts or whatever, I'll couple to the outer valley, so the single valley description is no longer good. But I'm never going to reach that energy, because the Coulomb is of order 30 to 60 electron volts. So if I look at low energy, these models, since they're continuum models, they are topological. They can be topological at any bandwidth. So basically, the moral of the story goes as following. How do you prove that these are topological? Well, you look at the representations at high symmetry points. And these are all graphene. You see the small moire. So at the K point, you really started. This is the K point of the moire. This is the K prime point of the moire, which is the K of the upper layer of graphene and the K of the lower layer of graphene. And these bands do this, and the bandwidth becomes shorter, smaller and smaller as I lower the angle, and you get flat bands. But the moral of the story is that you have a twofold degeneracy here, because you had a twofold degeneracy starting with the original Hamiltonian, okay, single layer graphene. This twofold degeneracy is this representation, which is called K2, K3, if you really are masochistic and want to learn a lot about the representations. All of these representations, you can find them on the Bilbao crystallographics server. They're tabulated now, and you can just find what they mean. But this is just a two-dimensional representation of the Dirac node of the original graphene, which remains stable after you twist the graphene. Now, Twisted bilayer has an extra symmetry, which is called C2x. Anyways, it doesn't matter. The point is that this particle hole anti-commutes with C2x. And then you can immediately fix the representation. So these are two bands, right? They're general points of two bands. They move up. I haven't plotted bandwidth here, so this can be 1 milli-electron-volt if you want. I just zoom in. So they move up and down, and at the gamma point, you have two one-dimensional representations, which I'm going to call gamma 1 and gamma 2. There, the plus and minus C2x has an eigenvalue, which is plus or minus. These are just the plus and minus eigenvalues, or irreps of C2x. And because particle hole changes energy into minus energy, these get flipped. Okay, so the positive energy is gamma 1, then the negative energy, which is related by particle hole to it, has to be gamma 2 because it anti-commutes with C2x. Same thing for the endpoint. Now, what this method wouldn't tell you, this is just a pure representation method. It wouldn't tell you if gamma 2 is above gamma 1 and gamma 1 is below gamma 2. It wouldn't tell you the order. But it would tell you that these are the representations that you have at the gamma point. And these are the ones that you have at the endpoint. So now you know the band representations at all these two flat bands per value per spin at the high symmetry points in the Moiré-Briand zone. And now it's a very simple thing to check the topology. And this is by now, there's a lot of theory behind this, but by now this is, again, tabulated. So do you go to the Bilbao crystallographic server and you check that server has all the atomic limits, i.e. all the localized orbitals. It has what eigenvalues in the Briand zone, bands that can be written down as atomical orbitals can give you. So bands that can be written down as atomical orbitals form a basis of atomic orbitals. And Bilbao crystallographic server has these types of tables. These are representations of bands at the symmetry point. So for example, what this means is that I add an s orbital at the center, at this center of the Moiré unit cell. So I'm trying to build an atomic limit of the s orbital here. This can only have these eigenvalues at the k points in the Briand zone. You see, is gamma 1 is the s orbital. It's a plus eigenvalue under C2x, etc. K1, etc. This one is a negative eigenvalue. Gamma 2 is a negative eigenvalue. This is a p orbital at 1a. Okay, so this is a basis of the atomic orbitals, or anything that you can write down in terms of localized Wannier states. Now look at our bands. Our bands in twisted bilayer have the following representation: gamma 1 plus gamma 2 at gamma, k2, k3 at 2, m1 plus m2 at the m point. This bracket just tells you the dimensionality of, so this is two-dimensional, so I have a Dirac point here. Okay, so basically you can see by just simple inspection that there's no way of writing these bands as sum of atomic limits. For example, if I want gamma 1 plus gamma 2, I could write them down in terms of an s at the gamma point, an s and a p orbital at this position, localized at this position, exponentially localized. This would also give me m1 plus m2, but instead of giving k2 plus k2, k3, the two-dimensional representation here, it will give me k1 plus k1, two one-dimensional representations at the k point. It wouldn't be my band that I want. So by just doing this inspection, the Bilbao crystallographic server has something that you can actually plug this in and it will spit it out, spit out the topological index, symmetry indicator, etc., however you want to call it, but it will tell you if it's topological or not. But basically, just by doing this inspection here, you can see that these ones, you can never write them down in terms of localized orbitals. So hence they're topological. And you can convince yourself that they're topological by just looking at the Wilson loop. And the Wilson loop is here, just taken in the Moiré-Briand zone, taken the Wilson loop in as, or the Berry phase. I have two bands per valley per spin. But I can take them up to any energy. So this is basically showing you that the Bicester-McDonald model is topological up to any energy. So here I'm taking it up to 100 milli-electron volts. I'm putting in 10 bands, not just two bands. Okay, just to just if you can 1, 2, 3 infinity. So basically, you can see here that if I take 10 bands and compute the Wilson loop, there's a winding in the Briand zone as I take the Wilson loop in one direction as a function of momentum in the other direction. So the Wannier centers can never be localized because they wind in the Briand zone. Okay? So that means that the system is topological to any bandwidth. And actually, this topology can be related to the following statement. The statement is that in any energy plus or minus E in the Bicester-McDonald model, you are going to find 4n plus 2 Dirac nodes. Not 4n, but 4n plus 2. Okay? And this 2 is just the 2 Dirac nodes of the original graphene. Okay? These are the 2 Dirac nodes of the original graphene. This is with particle hole. We can add particle hole symmetry breaking here. So this is this 2. And everything else in higher bands here comes a multiple of 4. Okay? Why? Because there are actually 2 per band, but you have particle hole symmetry, so there's going to be 2, at least 2 per band. You cannot have an odd number of Dirac nodes if you want gaps in your spectrum. And you have a multiple of 2 here, but by particle hole, a multiple of 2 here, so you have 4. And only these 2 bands, they have these 2 Diracs, which are zero energy, and you have this 2. So this is the topology of the model, is related to the fact that you have these 2 Dirac nodes of the original graphene model that are stable because of some other symmetry, C2Z times T, to twisting. Any questions? Yes?
This includes the particle hole symmetry? Because typically they only have the crystallographic symmetries, right?
That's right. So the Bicester-McDonald model at low energies, without relaxation, so without long-range tunneling terms. So it can include some relaxation. Relaxation just makes this W0 different from W1, as you know. But basically, that model has exact particle hole. So then you can, so in physics, what we want to do is start with the simplest model and then add complexity. We're going to add long-range tunneling, long-range, basically it's called non-local tunneling, which is relaxation, which is the term that breaks particle hole. And then you can have violations of this, okay? Well, we don't know the superconducting state, so I'm not sure if it's, we don't know what the superconducting state is. But basically, even though, one thing that I want to say, that even though you can add this long-range tunneling, non-local tunneling term, which make the band structure look particle hole asymmetric a little bit, the particle hole asymmetry in the wave functions is much less. So the wave functions still are almost approximately particle hole symmetric, not fully, even after these terms. Here, they're exactly particle hole symmetric. In the original Bicester-McDonald model, as was proposed in whatever, 2011 or 2013, I don't remember, those are exactly particle hole symmetric. Now, you know, ab initio results, Kaxiras and Lushkin and Koshino and Allen further did relaxation and showed that there's extra terms, and Kang and Buffett showed that there's extra terms that you can add to this, and those do break particle hole in the band structure, but not that much in the wave functions. Very good. More questions? Well, there's no point in going further if well, just everything is super clear, right? That's the reason for no questions, huh? If it's not super clear, there should be questions.
Symmetry also applies when you consider the rotation of the angles, like I thought it was
that's a 10 to the minus 5 effect. So neglecting those angles is a better approximation than neglecting spin-orbit coupling in graphene. So we already neglect spin-orbit coupling in graphene. That's a very, very small effect at 1 degree. Very good. Yes?
So with that inspection of the table, you can tell your bands are topological. Is that possible? You can predict what's the Chern number of your bands?
Yeah, so the total Chern number is 0 because they have, it's a very good question. The total Chern number is 0 because they have C to T times T, C to Z times T. That, the Chern number by itself is just the trace of the Berry curvature, and that's 0. But that doesn't mean you don't have topology. So, for example, you have 2 bands. So each of their Vania center, this is the winding. It looks like you'd have a quantum spin hole. So this is Chern number for, you know, if I plotted you a Wilson loop for the quantum spin hole and just gave you the Wilson loop, it'll look exactly the same because you have a Chern number plus for, say, spin up, Chern number minus for spin down. Or with time reversal if I don't want. But this symmetry does, this group is not the quantum spin Hall spin group. It's not the quantum spin Hall group. That requires t squared equals -1. Here, t squared is 1 because I'm looking per spin. I have no spin orbital coupling, basically. So it's not the group that would support quantum spin Hall. So it's a different type of topology, which is called Euler topology, which Bom Yang was also one of the, I'm not sure if I cite him. Hang on. I have to, okay. I'm sure I cite him somewhere, but basically it's called Euler topology, but it was thought at the beginning to be fragile. But particle Hall in the Bister-McDonald model promotes it to stable topology. Does that make sense? So you can't get it by a Chern number, but you can think of it as one Vanier center. You can think of it as two bands with opposite Chern numbers that somehow don't talk to each other. They actually do talk to each other, but you can you can think of them as not destroying the topology. Normally, if I just add two bands with opposite Chern number, unless I have t squared equals -1, which is the quantum spin Hall, I would break the topology. But this is the other case where I don't break the topology. I basically make an Euler class, which is C2Z times T is the one that protects this topology. It's a kind of very, very nice type of topology, I think. Well, I don't know if it's very nice. That's in the eye of the beholder. I find it very nice. Yes.
You say that like the wave functions cannot be exponentially localized because of the topological obstructions. Is the length scale of like these tails, is that the Moray or is that the atomic?
That's a very good question. So asking how much can these wave functions be localized is a very important question. So because that gives you the Hubbard view, and this is what the heavy fermion picture is trying to solve. So basically what we know is that for this class, for example, in 2 dimensions, you're always going to have some R squared tail, power law tail. You have to. This is like a Chern number class. You always have an R to the D or R to the D over 2. I don't remember. Maybe somebody in the audience knows better, but I think it's R to the D power law of the wave function of the Vanier states. You can never just localize them fully. But then you can ask, how much of the wave function can I actually fully localize? How much, what's the percentage? Because this thing has coefficients, right? You have a R squared tail, but you also have some exponential stuff, and then so this thing has coefficients. So you can ask how much of it can actually fully localized, and the answer is 95%, which is the reason for heavy fermions. So I'll just get to this right now. That's a very good question. So, okay, so basically, let me just point out some of the. Okay, so then, as the moral of the story is we have flat bands. They cannot be exponentially localized. We know that well, we know experimentally from experiments in, Ali Yazdani, Eva Andrei, Stefan Nash-Perge, many people, we know that at least spectroscopically, there's a large Coulomb interaction in these systems. And so the question is, we have flat bands with large Coulomb interaction that we cannot localize. So how do we describe them? And then if you look at the, initial experiments, this was, early in the days, I guess, you can see that there's something very weird about these initial experiments. So of course, the system superconducts, and it has metals, and it has superconductors, and it even has Chern insulators, etc., which are at some finite field or field-induced Chern insulators. But you also know that there's a set of experiments that, and there's more experiments that I haven't quoted here that are basically for graphing at a little bit different angles. And Ben was one of the pioneers in this that might change the story. So what I'm telling you now, it's an evolving field, might change in the next year. So do come back to the school so you can learn things that can change. But the moral of the story is that you can see 2 types of experiments, one of them showing clear delocalization, but then the other one showing clear localization of carriers. So for example, look at the STM of the charge structure of these systems, and you can clearly see charge localized on the A. This is the Moiré unit. Well, this is the Moiré unit itself, and you can see charge localized on the AA, the center of the hexagonal Moiré unit cell. And then you can see basically Coulomb blockade in STM, and you can see sort of unfreezing of local moments, what was interpreted as unfreezing of local moments in entropy experiments. Now, even with that, there's recent experiments that showed that this might happen in untwisted bilayer also. So that's another complication, but let's forget about that for a moment. So basically, you have two different types of experiments on these flat bands, some of which are telling you that you've got localization, and some of which are telling you that you have, itinerant carriers. So this paper by Shahalilani early in 2019 in this field basically tells you in the abstract what you need to, well, one of the things that you need to consider in this field. It tells you that the correlated states, here we should put S correlated states, feature a combination of contradictory properties, some associated with itinerant electrons, such as these ones, and other associated with localized moment. So this is in the abstract of this paper, and basically, if you look at the experiments so far, there is this dichotomy between localized and delocalized moments. So how do we understand this? And this is related to the question of how much can we localize out of these bands. And I want to point out that basically there is a mapping, which is just a unitary transformation of the low energy degrees of freedom that solves this problem. I'm not sure if it's the solution to the problem because it does depend on the coefficients of the problem. It does depend on whether we do have the correct values for the interaction. But what I'm going to say here is the following, that if this mapping turns out not to be the key to the problem, then it means that at least so far we've misinterpreted the value of the interactions in twisted bilayer, and we misinterpreted a lot of the experiments. So if you start from Bicester-McDonald model and follow through deductively, you should be able to get to this map without any approximations. If this is incorrect, then it means that we do not yet understand a piece of the physics, including basically the strength of the Coulomb interactions in the system. Okay, so what do we want to do? Well, what we would like to do is what was asked previously, is basically to understand really how much of these bands, which are flat, can you localize. Why? Because localized bands, if I have localized orbitals, these will carry the Coulomb interaction. So you want a real space picture that, Coulomb interactions are local, especially screened ones. And you want a Coulomb picture that basically takes into account that basically is local. You can work in momentum space, and you can do a lot of progress by just working in momentum space, but that obscures a real space description, and I'll show you that this real space description can be essential. So what you want to do is to build some sort of a unitary transformation, which is, Vannierization is just a unitary transformation. It's just that in flat bands, Vannier states and block states are both eigenstates. Doesn't happen in dispersive bands, but in flat bands, they're both eigenstates. So ideally, what we want to do is build a unitary transformation of these flat bands that basically makes the problem, turns the problem into a localized problem with a Hubbard-U interaction, and then we would know how to solve it because you have flat bands and Hubbard-U. Unfortunately, that's impossible because you cannot Vannierize these bands because these bands don't have localized orbitals. We just showed that they're topological. But actually, if you look at where the problem is with these bands in terms of Vannierization, is because of these eigenvalues at the gamma point. So these eigenvalues at the gamma point are the ones that don't allow you a Vannierization. Let me just point out that if these eigenvalues, you see at the gamma point, if these eigenvalues instead of gamma 1 plus gamma 2 were gamma 3, i.e. a two-dimensional representation at the gamma point, all these other ones would match. And this would be an atomic limit. What this crystallographic number means is the atomic limit formed by px and py orbitals at this Wick opposition 1a, at the center, in the AA position of the Moire-Briand zone. Why is this good? Well, we've seen where the charge is localized. It's localized at the AA position. So at least we know that we're going to get the charge localized correctly from STM experiments if we do this atomic limit. So all we need, so the problem is these representations of the gamma point of the flat bands don't match this one, okay? Don't match this gamma 3. They're two one-dimensional representation and not a two-dimensional representation, okay? The other ones at the K point and the M point, they match it. Okay, so that's the first piece of information. The second piece of information is that if you look very close to the flat bands, i.e. within an energy range that can be accessed by the Coulomb interaction, the Coulomb interaction, at least if we follow the STM experiments, is of this order of the gap between the flat bands and the conduction bands. If we follow this, then we can access these bands by the Coulomb interaction, or at least sort of there's no damage in considering them. You know, if the Coulomb interaction was a third of this band gap, then there's no need to consider them, and we would have to do things in momentum space. But here we can access it, and you can see that this guy has a gamma 3 representation. There's actually plenty of representations here. So I propose we take a Hilbert space that's contained, a low energy Hilbert space that's contained of, you know, plus 50 milli-electron volts to minus 50 milli-electron volts. This is accessible by Coulomb interactions, okay? So, and we try to perform a unitary transformation in this Hilbert space and see what we get. And this unitary transformation should be such that I can obtain flat bands which are exactly localized exponentially, coupled to some other bands that are not exponentially localized, so that in the end, I can reproduce the band structure of the Bista-McDonald model. Now, as I said, there's no purely localized Wannier orbitals, as was actually pointed out first by Kang and Buffek early on, just for these two bands per valley per spin. And hence, I can't do it just for these two, but I should be able to do it for the bands in 50 to minus 50 milli-electron volts, because I know that I can have the correct representations of building and atomic limits. And instead, and of course, actually, it turns out I can. So what you do is, for the people that know how to do this in ab initio, you take the projector into the bands from plus 50 to minus 50, you plug it into Wannier 90, and you ask to get the maximally localized Wannier states for, you build two trial Wannier states. So we sort of knew, I told you roughly what the localized orbital should be, because I have these K2, K3, M1 and 2, and gamma 3. I'm going to use the gamma 3 to make these bands trivial. So I told you these orbitals should be px and py, and really their representation in another basis is px plus minus ipi. We'll call these, by abuse of language, F electrons, or heavy electrons, and you'll see why immediately. And you can, choose these trial Wannier states, plug it into Wannier 90, and it'll give you localized orbitals of these, Hilbert space from minus 50 to 50, two localized orbitals. Now, of course, as you see, this has more bands. It has 2 plus 3, 4, 5, 6 bands per valley per spin. 2 of them will be px plus ipy localized orbitals, and then you can ask how much of these flat bands are made out of these localized orbitals. And this answers your question of how much they're localized. 95% of them are made out of these localized orbitals. Now, why is this not surprising in hindsight? It's very surprising before, but not in hindsight. In hindsight, this is not very surprising. Why? Because we know that when a band is far away from others in energy, it has to have almost no baryc curvature. We know that bands obtain baryc curvature by level repulsion, right? Level repulsion, opening gaps, whatever. That's the entire thing in baryc curvature. Now, if a band is far away from these flat bands, like here, for example, then a lot of these part of the bands don't have any baryc curvature. The only place where the baryc curvature, and I'm not talking about the trace of the baryc curvature, which is the Chern number. I'm talking about non-abelian. These bands really have a non-abelian baryc curvature. It's the off-diagonal component of baryc curvature. So it's, it's a little bit more, but it's, just going from abelian to non-abelian is just, playing with indices. So it's just another, it's just the off-diagonal component of the Fij, which is the Berry field strength. So basically, these bands here, they're far away. You see them 100 electron volts from here, and they're about 20 or 20, whatever, 22 from here. So most of the Berry curvature is actually concentrated here. So for most of them, you should be able to localize them, except something around the gamma point doesn't let you localize these Berry. Right? This is the same thing, for example, with how topology shows up by band inversion, right? I have a trivial band, then now I start bringing another band close to it at one point in the Briand zone. I flip the eigenvalues, I do band inversion. That's the point that's going to contain most of the Berry curvature or topology. Away from that point, if I don't have bands coming down, this band cannot feel any of the hybridization with other bands, so its Berry phases cannot change. So I expect most of it to be able to be localized, except for this point where there's band inversion and where you have topology. So basically, you know that the F electrons cannot have 100% of these flat bands. Why? The F electrons, or the Px plus IPI. Why? Because these F electrons, as I showed you before, will give you a gamma 3 representation here of these bands. But these are gamma 1, gamma 2. So the representations don't match. So they're exactly orthogonal at the gamma point, but they make up most of these flat bands. Now, why is this good? Well, the reason why this is good is that you can localize these F electrons within 0.2 of the Moiré unit cell, at least for the Princeton-McDonald model. So if you localize them within 0.2 of the Moiré unit cell, then it means that two of them at different Moiré unit cells, adjacent unit cells, will basically not be able to hop to each other because hopping is exponential. These are exponentially localized. These are exponentially localized Wannier orbitals, and they cannot hop to each other. And hence, this part of the Hamiltonian, which is I can write down my Hamiltonian as, this is the F. It's a 2 by 2 Hamiltonian because I have Px plus minus IPy, is 0 because it cannot hop 0 to 2 by 2. They cannot hop. So this is really the Schrödinger equation with an infinite mass localized orbitals. But we know that these electrons, these localized electrons, cannot make the entire physics of the flat bands because they give the wrong representation at the gamma point. You also know that what you did at the gamma point to obtain these electrons is to use one of the gamma 3 representations. Okay, so remember there was this band structure. This was gamma 3, two-dimensional. Gamma 3. So this is the Hilbert space that we use to Wannierize to obtain these F electrons. Here, gamma 1, gamma 2. I used, at the gamma point, I had two gamma 3s and gamma 1, gamma 2. I used one gamma 3 for the F electrons. So the remainder is a gamma 3, a gamma 1, and a gamma 2. And the reason why I'm putting them like this is because of particle hole. Okay? So what does this do? Well, gamma 3 is a two-dimensional representation, so I know it has to be two-dimensional, and these are one-dimensional. So I can just write the band structure of the remainder of the bands, and this is this. So this looks like a quadratic vortex, and this quadratic vortex should remind you of the 4n plus 2 that we said at the beginning. The topology is 4n plus 2 Diracs. A quadratic vortex is equal to two linear vortices added together. And this is just the band structure of untwisted bilayer graphene with some renormalized parameters. And this can be derived. It's not postulated, it's derived. I can take the Princeton-McDonald model, I can plug it, I can form trial Wannier states, plug it into Wannier 90, obtain these two heavy electrons, flat bands here, okay? Then I can do the complement of the heavy electrons and ask what it is and find out that I have to have a semi-metal, which is similar to the one in AB untwisted bilayer with a double vortex here because the double vortex is two Dirac nodes. Okay, so now you reached a very simple model where I have two heavy fermions here, which is Px plus minus IPy, and a double vortex here. This is gamma 1, gamma 2 representations. This is the I have here two gamma 3s, one from the PXPY and one from the double vortex. This is gamma 1, gamma 2. This is just the bandwidth of the Bicester-McDonald. So then you can tell me, well, this looks nothing like the Bicester-McDonald band structure, right? This has got, look, it looks very, very different. So, you know, you're telling me, you're basically selling me whatever lies, right? So this looks very different. It's got two heavy electrons and a double vortex, okay? But then the only thing, obviously, these ones would talk to each other, okay? In the Bicester, if I just derive their coupling term, you can derive it. We can also postulate it by symmetry, but you can derive it from the Bicester-McDonald Hamiltonian. And I can just tell you what it is. It's very simple. At the gamma point, okay, these form a gamma 3 representation, the heavy electrons, but these dispersive electrons form also a gamma 3 representation. They're the same representation. So then, two same representations allow you a constant term, gamma. This is a constant term. This is a number times the identity matrix to couple between them. And this number is exactly the gap between, in the Bicester-McDonald, between this bands, the next bands, and the flat band. Okay? So if you do this, if you now include this double vortex, which is this Hamiltonian, this double vortex is this Hamiltonian. It's a 4x4 Hamiltonian. It's got two here, a double vortex here, and one dimensional here, is this one. Okay, with a small mass here. Look, this is 4 me-electron-volts. This small mass is just the difference, the bandwidth of the Bicester-McDonald model. I can even make it 0 because it's very small, just for, you know, theory land. If I just include this, the F-electron Hamiltonian, they're very far away, the localized valence state, so it's 0, and they just couple with a gamma, with a just a number. Identity matrix between this representation of the Fs, which is the gamma 3 at the gamma point, and the C representation, which is also gamma 3. And now you can see the result. What will this do? These two gamma 3 representations, they'll do bonding and anti-bonding of these gamma 3 representations, move them up and down, and create these bands. So the band structure of this is the black lines, and the red dots are the Bicester-McDonald model. So now we map the problem into a very simple Hamiltonian made out of localized F electrons, 95% of them, and delocalized electrons with that carry the topology. These electrons have no topology. These electrons carry the entire topology. A coupling between them would give you an excellent match to the Bicester-McDonald model at low energies. So questions?
Construct this one for the F electrons and one for the C electrons?
Well, the C electrons are not atomic limit. So EBR means atomic limit, basically. So the C electrons cannot be an atomic limit because they carry topology. So that's why they're in the continuum. So the only atomic limit is the F electrons. But that's okay because they'll carry the interaction. If I make them local, so as a bonus of this, if you take the interaction, which we'll do in the next page, and project it onto this basis, the largest number will be on the F electrons. They'll be huge because those are the localized electrons, and hence localized electrons, localized charge carries most of the Coulomb. These are basically delocalized, and if they carry the topology. So I know I cannot make this model just atomic limits because it's topological at any bandwidth, at least the original Bicester-McDonald model. I know I cannot make it. So there's no way I can make it just a sum of atomic limits. So that's why I want a description of the flat bands, which are topological. So I pawned off the topology onto a dispersive electron, and I pawned off the interaction onto a local electron. The degeneracy of the K point is, so these F electrons are degenerate at the K point. They form the K2. They're a faithful representation at the K point. And basically, these bands, if you would write down this Hamiltonian, you'd have to add other plane waves. This band is a faithful representation. It doesn't break any of the symmetries, so you'll get the degeneracy of the K point. It just, here, in the zero hybridization limit, this is how the model looks when this gamma is 0, when I add no hybridization. Hybridization will just split these two gamma 3. There's two gamma 3s here, one from blue, one from red. You'll split them up and down. But here, you'll still have, it's just two-dimensional. You just don't see it because there's two of them. There's px plus minus IPY. They're on top of each other here. Okay? So it doesn't break any symmetry. Is it?
Or just a double layer?
So that's a very good question. So as long as your Berry curvature is very localized, you should always be able to do this because it's just the same. I mean, there's not much here. It's just this is just, turns out it just comes out naturally, but it should always come in any case. In twisted double bilayer, the Berry curvature is not as localized as here. So, it's the problem with Berry curvature not being localized is that you can always write down something like this, where you pawn off the topology on something else, but then your orbitals, your localized orbitals, are not going to be very, even exponentially localized, are not going to be very localized. So they're going to have some dispersion. So in effect, orbital models, for example, TMDs have orbital models. People write 2 orbital models, 3 orbital models of twisted TMDs. That's really kind of a vanirization procedure like here, but the orbitals, because they're not so localized in that case, the Berry curvature is actually more spread out. That's probably one of the reasons why we get FCIs in TMDs and not here. Then those orbitals are not, they talk to each other. So you don't have this separation of scales where one carries the Coulomb interaction, the other one carries the itineracy, which is essentially if you want to make this unitary basis transformation. It just tells you that, this unitary basis transformation is not very useful in the other cases. But in cases where the Berry curvature is very localized, or non-abelian Berry curvature, you should always be able to do it, because away from where the Berry curvature is localized, you have no Berry phases, and that means you can localize that part very well. Make sense? Thank you. Yes?
How well do the form factors match?
Oh, they match this. I mean, depends, in this plus minus 50, they match extremely well. Now, if you go to higher things here, they'll match worse and worse, right? But higher things here, I'm not interested in because the Coulomb cannot get me here. But also, you can have these ones match really well if you do more k dot p expansion. So this is just the first k dot p. But I can add here, k to the third, etc. I can make my C electron not just be linear. So if I add k to the third, for example, I could reproduce even this. Okay? So that model that I showed you, if I would show you with just k linear here, if I would show you the band structure here, you wouldn't see this one. Okay? This one going down here. But if I add k squared, I could, or k cubed or whatever, if I had the next order, I could reproduce this. But within plus minus 50 electron volts is a faithful description that matches the form factors very, very well. So within this energy range, the form factors, everything, velocities, energetics, form factors meaning just overlaps of integrals, matches extremely well. And you can actually get the form factors because this is a model that you can diagonalize, and you can get the form factors from that model. So then you can use those form factors, for example, in momentum space calculations if you want to, of this thing. So they match very well to this because it's derived, right? It's not postulated. We derive it from the, it's derived from the Bicester-McDonald model. Very good questions. More questions?
If you start from your CF model now and introduce the topological phase transition where you disentangle these bands, would this also happen in the C and F electrons?
So in this particular case, it's a very good question too. In this particular case, you can't disentangle the bands by keeping the symmetries, because I showed you that the model is topological at any bandwidth. And that's really just, so in this Bicester-McDonald model does not, you cannot make these bands non-topological. If you could, in the original Bistrom-McDonald model, if you could, it would contradict what I've said so far. So in this case, I cannot make a disentangling transition. What happens if I close this gap to make it, and then I would close this one, so I get two topological factors, which leaves me the band still topological afterwards. So in this case, I cannot do it, which is really the reason why this can be described by, this has to be described by a C electron, which is a continuum electron, and this double vortex is really the topology of this C electron. Now, generically, if I have the Berry curvature, so generically what I would do, for example, let's just take a topological insulator. So let's not take this particle hole symmetric. Let's take a topological insulator and assume that I've made this band flat. If you don't have this band flat, if a band that you're trying to describe the physics of is not flat, then this model is useless anyways, because dispersion, you have a Fermi level, dispersion will not let you, or quasi-flat, would not let you localize it. But let's assume this band is flat and trivial, okay? So localized exponentially. Now I bring another band from here, okay? And so if it's trivial, I have localized Vanni orbitals, okay? But I bring another band from here and I close this gap slowly, slowly, slowly. Then originally this had to be an F electron because it was F electron by abuse of language, meaning localized electron, because it was very localized. And then I'll just couple it, I have F dagger F with a 0 probably if it's flat because I have no hopping. But then I bring a band K squared over 2m, okay, C dagger C plus delta F dagger F, F dagger C. Okay, so I can, if I now make a band inversion, I can go topological. So it's not only topological bands, but trivial bands with a small bandwidth, with a small gap to dispersive bands that can be described by this. In fact, we know this from the Anderson model. Anderson model is just the model of d electrons really coupled to a quadratic band. Back in those days, they didn't know very much about topology, but this is the same thing as that, except we added topology. Yes?
And open up the gap in the F electron part. Still is correct. You can also use the same picture.
Yeah. So basically, for example, you can add strain, and I'll show. Well, I don't think I'll get to strain. But what happens is a very good question. What happens? So here. So these are. So this is what I'm saying that if this picture turns out not to be correct, then we're missing some interaction, missing some part of the physics. Either either the Bistrom-McDonald model is not describing the system or the interaction is lower. So far I didn't get to interactions. But basically, if you add HBN or strain, okay, then I can still vanniarize the Bistrom-McDonald model with strain, which in the continuum version is a Kangen-Wafek model that you can you can still vanniarize it and obtain Vannier states, and you find out they're similarly localized. In fact, the localization almost doesn't change, just because you're basically dealing with the physics of a very dispersive band close to flat band. So if these, as you know, strain will just split these flat bands into, one and another one, split by 10 me-electron volts or whatever, 4 me-electron volts per 0.1% strain. But splitting these by 10 me-electron volts here is not going to change the fact that they're separated by 100 me-electron volts from these bands, just because these bands have the same velocity as the original graphene. So they're very dispersive. By the time you reach the end of the Moiré-Briand zone, these have gone up to 100 me-electron volts. This cannot change. So this part, with strain or without strain, still has to have zero Berry curvature, or zero Berry winding of Berry phase. Still has to be a localized state. And indeed, what you find out that if you add strain, the only thing you need to change, and since I won't get to it, I'll just say now because it's the only thing you need to change to take into account strain is instead of 0 here, you put epsilon xy times sigma x plus epsilon minus, which is epsilon xx because it's heterostrain, epsilon xx minus epsilon yy times sigma y. So you just split this. You see, this basically splits this. So let's just put epsilon xy. This just splits this to plus and minus epsilon xy. And then 95% you can model the Kangen-Buffet or Caxiras or Cochino models. Make sense? Have I answered your question? Very good. More questions? You sure? No more? Oh, really? Oh, wow, okay. Well, again, very good. Okay. So let me just tell you the last thing then. The last thing is that now you can take the interaction. Okay? And what you take is the Coulomb interaction, and you just project it on this basis. You have expressions of this basis. You can have that numerically, you can have it analytically, you just project it on the basis. And then what you get is the following. You get the following terms, but really the most important one is that you now see that all your interaction has gone into the Hubbard U of the F electrons. So now you have really what's called the Anderson model. So this is the original Anderson model, except Anderson didn't look at the topological model. So what you have is an Anderson model that instead of having a k-square dispersion of the light electrons, has this double vortex here. And also you get some extra interacting terms. Now this might look like a nightmare to solve because it's a many-body model, but this system has several things on top of the Anderson model that makes it easier. For example, these light electrons, even though this is a quadratic touching, this mass is very small, so it's very little density of states. So it turns out you can do things with this that are more accurately numerically than Anderson model, such as DMFT. And this is hopefully where we hope to solve this model. And, well, there are some solutions to this model. We don't know if they fully match the experiment, but hopefully they will. What I wanted to first show you very quickly is that this can at least match Ali's data and some new data. I'm not sure if it was told by Eva Andrei, if her students are here. I was told that I can show some of her data. Anyways, if the students are here, then maybe rush to publish. But basically, you can see kind of like, in this original STM plots of Ali's, you can see the appearance of these Hubbard bands. These are kind of Hubbard bands, but then you can see things that look like the Kondo resonances. And this is, typical of the physics of the Anderson model. You can get Kondo resonances in some regimes. And one of the, hopes, of this physics is that superconductivity could appear out of this Kondo state, which screens the Coulomb interaction. So the massive question in the physics is about superconductivity and what screens the strong Coulomb repulsion to get attraction. And the hope is that the Kondo state that I didn't get to talk about, that's shows up in Anderson models and turns out shows up here in the theoretical calculations, can provide the screening of the Coulomb interaction. So with that, I thank you for your attention.
Due to the limited time, maybe you can just take one question.
Yes, one question. Make it good.
You said in the beginning something about understanding the Hubbard model. So do you think that is related to what you just said?
I mean, I think basically, so there's many layers of this question. So for example, layer one, where is it? Maybe I didn't get. Layer one is that these are complicated models. So there's many methods of doing them. King method of Anderson model is DMFT. DMFT is a local approximation. There's another method called the Gutzwiller approximation. Turns out that if you use them on this model, they don't agree. And one of them, which was thought to be the weaker one, which is the Gutzwiller approximation, agrees more with with one experiment. They don't agree with Ben's experiment. They agree with one experiment, but the samples are different than the DMFT. Okay, so the question is, all these are approximations done by very smart people over time. So the question is, can this actually tell us which approximation is correct and which one to use it in many-body systems by doing the comparison theory to the experiment? That's a wishful thinking, kind of like peace in the world. But hopefully that's one of them. Now, if you really want just the Haber model physics, the Haber model originally is topologically trivial. So you have to find topologically trivial bands, which I think twist and be able to tune them. So you need them twisted. Otherwise, otherwise you won't be able to tune them, which I think we're close to doing. So in that case, it will be a Hubbard model simulator because the band will be trivial. In all these cases, the band is topological. So you have some sort of a topological Anderson model. But I think you can learn a lot about, right? Cold atoms was always put to us as the laboratory where we can test Hubbard models, etc. It turns out that maybe these ones are equally good, or I don't want to say better, but certainly there's another avenue that you can with even more controllability. Hopefully, I don't know. It's not. It hasn't panned out, but one can always dream. I think it's a very exciting field, right? Because you can do a lot of things, but people just need to push.
That's